In our previous video, we looked at equilibrium and what dynamic equilibrium is and what we see in the chemistry reactions, so that they're reversible reactions and that the rates of the forward and the reverse reactions are equal. Now we're going to look at some factors that may or may not affect the equilibrium. So we're going to look at each of these different things that might affect the solution equilibrium. Not all of them actually have an effect, but we're going to look at each one individually. We'll start with the effect of changing the concentration of the reactants and or products. Then we'll look at the effect of heating the solution or cooling it. We'll look at the effect of a catalyst, the effect of the particle size, the effects of stirring, the effect of pressure, and finally the effect of volume. In these cases, we're looking to see things that affect the rate of a reaction, and it has to specifically affect the rate in only one direction, because otherwise we're just doubling the speed of both of them. We're still at equilibrium. I'm going to start with the one that has the largest effect, and that is the effect of changing the concentration of either the reactants or the products. This is the one that you will definitely see on exams and quizzes, so make sure that you understand this one in particular. We're going to use the same reaction we did before, where we have A and B are reacting to form C and D, and of course the reverse reaction is happening at the same time. We're going to start with this system at equilibrium. Remember, that does not mean that there are equal amounts of reactant and product, just that the rates of reactions are going the same. So currently in the container we have all four species, A, B, C, and D, in different amounts, but we have all four of them. What we're going to do is we're going to add one of them. So let's just go ahead and add some A and ask, what will it react with? Hopefully you can see it's going to react with B. If it reacts with B, then the amount of B is going to decrease. B is going to go down. Because they reacted, it goes away and it turns into C and D. And so that means that C and D are both increasing. And that means that the addition of A has shifted the equilibrium. The numbers are not going to be the same. It's going to shift it from reactant towards product, and so we're going to say that it has shifted to the right. Now let's look what happens when we add B. So if we add B, it's going to react with A. So that means that A will decrease because it's reacting, and it's creating more C and D, so C and D increase. That means that this reaction is creating more product, so that means it's shifting to the right. And what happens when we add more C? If we add C, it's going to react with D, so D will decrease, and those two are going to make more A and B, so that means that the reaction has shifted to the left because we're making more reactants. I'm going to have you try the last one, which is to increase the concentration of D and decide which way does the reaction shift. Pause your video and then come back and I'll give you the answer. Hopefully you can see that increasing D means that it will react more with C, so C will decrease, and it will create more A and B. They'll both increase, which means that the reaction has shifted towards reactants, saying that the reaction has shifted to the left. I'm going to give one last example, and in this case I'm not going to be increasing the concentration, but I'm going to be decreasing the concentration of something. Let's look what happens when we decrease the amount of C. Well, in the reaction, it's going to do everything it can to fix the thing that you just did. And what will happen is A and B will continue to react, and they're going to react faster because the C and D reaction is going to go slower because there's a lower concentration of C. So A and B will go now faster, making more of D. It's also going to be making more C, so it's going to come back up. But it'll still be an overall decrease because I removed some of it. And that means that the reaction has now shifted to making more product, so we're going to say that it has shifted to the right. We use this in chemistry in real life because oftentimes we want to sell something, we want to make more products, we want to make whatever it is we're trying to make. So what we can do is we can remove one of the products and it'll make more and more of the other product. It's actually going to make more of both. There are a few ways that we might remove a product. One of them is to form a gas. So if it forms a gas, the gas bubbles away. That means it's not in the container anymore. It can't react with D, so the reverse reaction can no longer occur. This is one of the ways that we get a one-way reaction. And you'll see that in those reactions where we form a gas, the reaction is not at equilibrium. It's going in one direction only. Another way would be similarly to form a solid. The solid precipitates at the bottom. It's sitting on the bottom, has a very hard time reacting because it's in this lump at the bottom. And so that slows down the reverse reaction, and the forward reaction continues. And again, we tend to get one-way reactions when we form a solid. And I'm going to see that again later when we talk about how to predict whether the reaction goes to completion. Some other methods might be to boil it off if it's a liquid, to trap it or to react it with something else so that it's trapped, and that pulls one of the products away, allowing us to make more of the other product. All of these changes follow a principle called Le Chatelier's principle. Le Chatelier's principle states that if a constraint is applied to a system in equilibrium, the equilibrium will shift so as to tend to counteract the effect of the constraint. Things that are considered constraints are things like a change in concentration, as we've just seen, a change in temperature, a change in pressure of either the reactant or the product. And it simply states that if we change something, that the equilibrium will shift to fix it. So whatever we do, we're going to change the equilibrium a little bit. It's going to change to fix whatever we just did. If I increase one thing, it's going to decrease it to make it closer to the equilibrium value. And that shift will affect all of the chemicals in the reaction. So it'll affect everything. So that means that the equilibrium will be shifted in one direction or another, depending upon the concentration, the temperature, the pressure, those types of things. So let's continue by looking at the temperature, pressure, and other factors that might have an effect on the equilibrium. Let's start with temperature, and for that we're going to look at the effect of heat. Specifically, we're going to look at the heating of a solution, but we could also look at the cooling of a system. What is particularly challenging about looking at the effect of heat or raising the temperature, the final effect on the equilibrium will be dependent upon whether we have an exothermic reaction or an endothermic reaction. So let's remember what that means. In this reaction where we have A and B make C and D, if it's exothermic, that means heat is exiting the system, which means that the heat is a product of the reaction. On the other hand, if it's an endothermic reaction, we have A and B going to C and D, and now heat is a reactant rather than a product. Let's see how that affects the equilibrium. First, we'll look at the exothermic reaction where heat is a product. If we add heat to the system, we're going to see that C and D will both decrease because they're going to try to fix what the added heat was. So we're going to try to fix that, and that means that the equilibrium will shift to the left, creating more A and B, creating more reactant. So we have a shift to the left if we add heat to an exothermic reaction. And so what happens in an endothermic reaction? In this case, the heat is a reactant to the reaction, and so we're going to see an increase in the heat. By increasing the temperature of the reaction, we'll decrease A and B and increase C and D, meaning that the reaction is producing more product and has shifted to the right. And of course, you'd see the opposite effect if the reaction were cooled rather than heated. And in this course, you won't be expected to know about the effect of heat on the equilibrium for the exam, but in lab, you'll be checking this out. Now let's look at how a catalyst might affect the equilibrium. So let's first define what a catalyst is. As you recall, a catalyst is any substance that increases the rate of a reaction without itself being used up. And so it's important because this does affect the rate of a reaction. And we'll look at how a catalyst increases the rate of reaction to see what effect it has. So you might recall that I gave this example of how a catalyst works. I was riding my bike from California to Missouri, and I had to go up and over this hill, and that took a lot of energy. And my sister would come back and visit me, and she'd go from Missouri to California, and in this case it would take a little bit less energy because this was an endothermic reaction. In any case, we're going to go back and forth, and the two of us are visiting each other back and forth at equal rates. So I'm going once, and she's coming the next time, going back and forth at equal rates. What a catalyst did was like a tunnel. We added a tunnel in. so that I could get from California to Missouri faster. And how it increased the rate was by lowering the activation energy, making it a little easier to do. Now, what about the person going from Missouri to California? Well, it also lowered the activation energy by the same amount, and so the increase in rate occurs in the opposite direction also. What this means is that by adding the catalyst, we're increasing the rate of the forward reaction, but we're also increasing the rate of the reverse reaction, which means there is no overall difference in the forward and reverse reactions. And that means that there is no effect on the equilibrium by adding the catalyst. The equilibrium will remain the same even in the presence of a catalyst. Previously, we saw that the size affected how fast something dissolved. So we saw that in this sugar cube, it dissolved slowly because it had a very small surface area, and this larger granulated sugar dissolved much faster because there were lots and lots of areas that could come in contact with the water. And according to collision theory, for a reaction to occur, the particles have to come in contact with each other. We can see that particle size could have an effect on the reaction rate. So what we know is that the smaller the particles are, the faster a reaction will go, which means it has an increase in rate. So by crushing the size of the particles, we can increase the rate of a reaction. And that's certainly important for our equilibrium, which reaction's going faster. One of the ways that chemists try to make a reaction go even faster is to dissolve those. So we generally will be using solution chemistry because when the solid is dissolved, now it's in individual ions or particles and not even as big as a granulated sugar, let's say. So it's now going to be much, much smaller particles, and that is the way that we can increase the reaction. So in this class, all of our reactions are going to be solution chemistry, so we're not going to be really looking at the particle size specifically. I won't be asking you any questions related to that, but do know that as I produce a product that is a solid, that particle size gets larger and larger, which means that the reaction in the reverse direction gets slowed down, which says that we're making more and more of a product, and that is when we talk about the reaction going in one direction. If we form a solid, that reaction goes in one direction because it has a hard time going in the reverse reaction because of the particle size. Again, I won't be asking you this specifically on tests, other than to say that equilibrium is not affected by particle size. Now let's look at the effect of stirring a mixture. So I've got this solution already ready to go. We know that stirring will increase the rate of dissolving, but doesn't increase the rate of a reaction. We do know that the reactions have to come in contact with each other. So if we have a solid at the bottom, stirring will probably allow that to go a little faster. But in this case, we don't have any solid on the bottom. We're going to be looking at, in our reactions, all of them are solutions, which means everything's dissolved, and so we see that there's no effect on the equilibrium. And now let's look at the effect of pressure. Because pressure has such a strong effect on gases, but not much of an effect on liquids or solids, it turns out that pressure only affects systems that have gases present. So we're going to be working on solutions in our course. We're not going to be looking at gases in general. And so we're going to see that that effect is minimal for anything that we do in our class, and you will not be tested on the effect of pressure. But what happens if there are gases present? When we look at an equation, we're going to be looking to see where is there more gas. The more gas there is, the more effect pressure will have on that side. So an increase in pressure on the side with more gas will cause it to try to fix that and decrease the pressure by making the reaction go in the other direction. So let's look at this example. Here we have 3 moles of hydrogen reacts with 1 mole of nitrogen to form 2 moles of ammonia gas. Notice that these are all gases, and we're basically going from 4 moles of gas on the reactant side to 2 moles of gas on the product side. If I push down on this, it's going to try to fix this by making less gas. That means that the reaction will shift from the reactant side to the product side to relieve the pressure caused by those gases. And of course, if I release the pressure, it's going to go the opposite direction and it's going to create more reactants. And what happens in this reaction? Here I have 2 hydrogen chlorides and 1 sodium sulfide, and that's going to create hydrogen sulfide gas and 2 sodium chlorides. Now in this case, I only have the hydrogen sulfide as a gas. So that means we only have to look at the pressure on the product side. If I increase the pressure, this reaction will go in the backwards direction, meaning that the reaction will shift to the left, making more reactants as I increase the pressure. Decreasing the pressure will allow us to make more of the H2S gas. Again, this is only important for reactions that have gases present. If there are no gases, there's no effect due to the pressure. And now let's look at how changing the volume might affect the equilibrium. In this case, we have 2 different ways that we can change the volume. In the first instance, we might change it without changing the concentration. That means I'm pouring out a glass of the solution and another glass of it, exactly the same substance. I haven't changed what it is, so the solution concentration is exactly the same. In that case, there is absolutely no effect on equilibrium. So even though I have twice as much stuff, the reaction is not going to go any faster because the concentration remains the same. So that does not have an effect on the equilibrium. On the other hand, if we change the concentration while we're changing the volume by either adding more of the solvent, like water or air or whatever it is, or by removing some of the solvent, so we're changing the concentration, which also changes the volume, then we can see that there will be an effect on equilibrium. But to understand how the change in concentration changes the equilibrium, we would actually need to do a lot more analysis of the material. So in this class, we stop here and we are going to assume that if we change the volume, that we are changing only the volume, not the concentration, in which case there is no effect on the equilibrium. So what do you need to know overall about equilibrium? Number 1, you need to know that the equilibrium means that there are equal rates of forward and reverse reaction, and it has nothing to do with the amount of reactant or product present. It just says the rates are going the same speed. The second thing is that if I change the concentration of a reactant or a product, it will shift the equilibrium. You need to know how to predict which way that equilibrium will shift. You should also know that catalysts do not affect equilibrium. You will not need to know about the effect of stirring, pressure, temperature, and volume